Alright, let's talk about definite integrals. So a definite integral from a to b of f. Don't forget the dx when you write it out. Anyway, you can find it numerically like this. So you find an antiderivative to little f, namely capital F. You write out this middle step, please, and then you just plug in b minus plug in a. And this definite integral of f from a to b represents the signed area between the graph of f and the x-axis from a to b. Okay, here's the task. Find the area enclosed by the graph of y is x plus 1 and the graph of y is 2x minus 4 and the coordinate axis. So obviously you want to make a picture. 1, 2, 3, 4, 5, 6. 1, 2, and so on. Okay, so let's see what's going on. This line has slope 1, y-intercept 1. So it's going to look like this. This guy has slope 2, y-intercept minus 4. So it's going to look like this. And obviously this is the y-axis, this is the x-axis. So here is your area. Now, where do they intersect? Here. What's the x value there? Well, x plus 1 is 2x minus 4. X is 5. This is 2, because 2 into this function gives 0. Here we have 0.1. But anyway, so we're going to divide up the area into two parts. This is the area 1. This is area 2. Area 1, this one, is just the area between the red graph and the horizontal axis from 0 to 2. So it's the integral from 0 to 2 of this function x plus 1 so it's 2 plus 2 minus all of 0 plus 0. Yeah, I know it's 0, but I'm going to write it out because I want to emphasize that you need the brackets. Area 2 goes from 2 to 5. And the function which goes in between the integral sign and dx is the difference function of the red graph and the red function and the black function, because we want the area between these two. So you take x plus 1 minus all of the lower function. So note the brackets, because now this is x minus 2x, that's minus x, 1 minus 4, so when you take away the bracket you get a plus 4, so it's plus 5. Now we just, the rest should be standard. Plug in 5 minus all of what you get when you plug in the lower limit. 2. Again, please note the brackets. So this is 12.5 and this is minus 8, so it's 4.5. So answer is 4 plus 4.5, 8.5 area units. You could have argued geometrically. Ding, ding, somehow ding, by triangles and rectangles, but the point of this exercise was to practice on this here. So demand and supply. So as we saw last term, at the equilibrium point, demand and supply quantities coincide there, so we get a system at the equilibrium point. Please write this out explicitly. Solve it to get the equilibrium point E with q coordinate q star, say, p coordinate p star, say. Q star and p star are numbers, elements of the set of real numbers. This term we also learned about consumer and producer surplus. So if this is the situation, remember in economics people put price on the vertical axis or quantity on the horizontal axis. Here supply graph, demand graph, equilibrium point E. So Q star, P star. Producer surplus, that's this area. Consumer surplus is this area. So you integrate to find them. To find the consumer surplus, you integrate the difference between the demand function and the constant function P star, and you integrate from 0 to Q star. Producer surplus is a similar story. Let's find the indefinite integral of 1 over 2x plus 12 by using a substitution. So u is 2x plus 12, then we use Leibniz notation. Du dx is 2. So du is 2 dx, and hence dx, which is what we want to translate, is half of du. Alright, so this is our working box. And then down here I'm going to continue the real stuff. So 1 over 2x plus 12 becomes 1 over u, dx becomes half of du. This integral now, well, the half just hangs around. 1 over u integrates to ln of the absolute value of u, and then plus c. And now recall that when you give the answer should be in terms of x, because the question was in terms of x. So there we go. Again, with indefinite integrals, don't forget the c. When an integral is not trivial to handle, when you cannot immediately think backwards, you should try maybe substitution, maybe integration by parts. For this one, it stinks that you should use substitution, because if you put u, if that's your new letter, if you let that be x4 plus x plus 5, obviously this can be translated to the u world, and then what remains looks like the derivative of u, which is good news. So here are the details. Remember to use the Leibniz notation for the derivative of u. So it's 4x3 plus 1, because now the du and dx pop up. You can treat it as a fraction. So moving the dx over to the other side, this is what you get. And you kind of wanted to translate 8x cubed plus 2 into the u world. So let's multiply by 2, and there you go. You have 8x cubed plus 2 times dx. So you can translate that into the u world as well. And what about 530,711? Well, I included that because it's my favorite number. No, it's actually not. But numbers are nice, so they just hang around. So this is going to be our working box, and then we really continue down here. So this becomes u squared, 8x cubed plus 2 all times dx, that's 2 du. And then the 530,711 just hangs around. Now, you must also translate the limits of integration. So let's do that. When x is 0, u is what? Well, when x is 0, u is 0 plus 0 plus 5. And when x is 1, u is what? Well, when x is 1, u is 1 plus 1 plus 5. That's to say 7. So the new limits of integration are 5 and 7. So it's kind of easy to forget to translate the limits of integration, but it's of course crucial to do it. Now the rest is simple. And the whole point of making the substitution was that treating the integral is easier when you're in the u world. And now, since we have definite integrals, you don't have to go back to the x world as you do when you have indefinite integrals. Now you just need to plug in the upper limit minus the lower limit. And it's 343. If you don't know it by heart, it's like 7 times 50 minus 1, so it's 343 minus 125, so it's 218. And assuming that that guy down there is not yeah, whatever. It's time for some integration by parts, IVP. Let's first do the indefinite case. So here's the formula. It's basically the product rule backwards, so you can use it when you want to integrate the product of two things. I mean, it might not always work, but you can try it. So what's going on is that one of the two guys gets integrated here and here, whereas the other one stays the same here, but in the new integral which you have to deal with, u has been differentiated. So you want to pick u so that it stops being annoying upon differentiation. Pick u so that it stops being annoying upon differentiation. In Sweden, you might see the formula like this. It's exactly the same. One function gets integrated in both spots, the other one stays the same here, but is differentiated in the new integral. Let's do a practical problem. Here you have a product of two functions. It's the 6x is annoying because you cannot immediately think backwards, but if you could differentiate it and get 6, that would be nice, because 6 is a number and it would just hang around. So on the side here, I will write what I'm going to use. So ux will be 6x, the thing that stops being annoying upon differentiation. And so since together they got to multiply together to this integrand, the prime x has to be e to the power of x, and then the x is found by integrating this. But that's so simple to do that you can do it in your head. And you don't need C when you do an IVP. So by integration by parts, this becomes ux times vx minus the integral of vx times the derivative of u. And here, the u stuff after differentiation is no longer annoying. We have 3x e to the power of 2x minus the integral of 3 e to the power of 2x. And that is a nice integral, because here you can just think backwards immediately. Don't forget the c, which stands for an arbitrary constant when you give your answer.